This video is going to cover section 3.6, arguments and Euler diagrams. Okay, so in this section, we're going to continue off of section 3.5 and speaking about arguments and whether they are invalid or valid. We're going to do that using something called an Euler diagram, which is these four different boxes you see here. Okay, an important thing to notate here is that we are going to be using something called a quantifier, which we saw in previous sections. Quantifiers include the words all, some, none, which is the same as no, okay? And the way it's going to work is if you see any of these in the premises that we have, so remember like that first sentence, then we would look at one of these four different diagrams. So for example, if you had that all cats are animals, okay, you would be looking at, let me see, you'd be looking at this one right here, because all cats are animals falls into this pattern of a statement, okay, all P's or Q's. And if that's the case, this is what the diagram would kind of look like, okay? The circle in the middle, so this little circle that you see like uh, in some of the circles, this is the conclusion. So this is what we usually find at the end of an argument and what we're looking to see if it's valid or invalid. Okay, so we're going to go ahead and jump right into an example so you can see how we use these patterns here to figure out whether an argument is valid or invalid. Okay, so here's our first example, and it's actually already done for us. I went ahead and did some of the legwork for us here. We have the word all, okay, so keep that in mind. It says that all college courses are fun. So what I did is I went ahead and said, let's do college as our P's and fun as our Q's. Okay, this course is a college course, therefore this course is fun. So this follows the all P's or Q's pattern, which is this box right here. And I'm just getting this directly from the four possible scenarios that we have here. Okay, so it's the first one. So if it's going to be this one, according to premise one, so this is our first premise. Okay, that's this one right here. This is our first premise. All college courses are fun, which means that all the P's, which is this yellow circle, are going to be inside the other circle, the Q circle. So I have that here. College courses are inside the fun courses. Okay. The second premise, the second premise is that this course is a college course. So this course is going to be inside the P. Okay. So it's somewhere in here. I don't know where it's at, but it's somewhere in there. And then our conclusion is that, therefore, this course must be fun. So this right here is our conclusion, these three dots. This course must be fun. So this second part, this second diagram here, remember that dot has to be in here, shows us that the college course is in fact inside the college course circle, because that's where it should be. And if you look at the bigger picture, that circle, since it's in the middle here, it's also in the fun circle. So therefore, this is a valid argument. Okay. Now to check this, we want to say, well, can I put this course anywhere else? If I could put that dot somewhere anywhere else, that's not inside this yellow circle, that would prove that this is an invalid argument. So we're going to check that. If I were to put my circle here, my little dot, my conclusion, okay, well, now that conclusion is no longer a college course. And according to the second premise, it says this course is a college course. So we can't do that. We can't do that there, okay? Can we put the circle out here in the universe? Well, again, it tells us that this course is a college course. So it has to be a college course. So we can't put it out there either. So that means it has to be somewhere in this space right here. And because this space is inside the bigger space of fun, that means that this course is fun. Okay. All right, let's try another one, see how this works. So we have another example. All lawyers drive BMWs. Susan is a lawyer, therefore Susan drives a BMW. So we're going to go ahead and try to make our own Euler diagram here. So we start with the box, okay? And we're going to color code this a bit. So we have that all lawyers drive BMWs. So I'm going to do my BMWs here. So let's go ahead and do that. So there is my BMW circle, okay? And it tells us that all the lawyers drive BMWs. So that means that my lawyers are, they're in here somewhere. Okay, I'm gonna kind of do a line there. Those are the lawyers. And if you're not sure where to start, that's what these diagrams are for. Okay, that's what this one is for. Okay, this is the pattern all P's are Q's. And if we look at our example, we have exactly that. All P's are Q's. All of this are that, or all of this do that. Okay, in this case, drive. Then we have our second premise. Susan is a lawyer. So Susan, I'm going to do her in blue right here, this light blue here. Susan is a lawyer. That means she's got to be in here somewhere. Okay. Therefore, Susan drives a BMW. So this is our conclusion. So does our conclusion match where the dot is at? Well, let's see. Susan drives a BMW. I'm sorry, Susan is a lawyer, so she is in the right circle here. She's in the circle. And it says that she drives a BMW. Well, this circle is also inside the circle of BMW. So that means that yes, Susan does drive a BMW. So this is a valid argument. Okay, much quicker than a truth table. Let's go ahead and do one more of these. Okay, and I went ahead and included the diagram for your reference. This one says that some Impressionist paintings are Renoirs. I hope I'm saying that right. Dance at Bougival is an Impressionist painting. Therefore, Dance at Bougival is a Renoir. So let's try to draw this. Okay, we have our universe here, which is this big box, and then we have our reference chart here. We have that some P's are Q's, which is exactly what I see here. Some this or that. So I know for sure I'm going to have two circles. Okay, I'm going to have two circles here, and they're going to overlap at some point. Okay, so let's say that the Renoirs are the purplish pink color. So this is the Renoir, or Renoir, I can't say that, whatever that is. And the Impressionist paintings are the other one. So that's this guy right here. Impressionist paintings. Okay. So since some of them are in there, that means we're just talking about this piece right here. Okay. This little part where they overlap. That's the sum that they're talking about. I guess I can color code that. That's this part right here. Okay, that's the sum. Our second premise says dance at Bougival. So that's I guess some painting is an Impressionist painting. So then let's do this color. So this guy, we have some painting, and now it doesn't really say where the paint. It just says it's an Impressionist painting. So that means that I could have him here. I could have it here, but I could also have it here. Okay, so just keep that in mind. The conclusion is that this painting, Dance at Bougival, is a Renoir. So it's saying, well, it has to be this one. Okay, but what happened here? Is it possible for the conclusion to land over here for this painting to be just an Impressionist painting and not necessarily a Renoir? Well, yeah, it is possible. So that means that this statement right here, or this argument, I should say, is an invalid argument. So if you have more than one space, you can put that premise, that second premise, okay, while still following, making sure that these both conditions are met. Okay, that makes this an invalid argument. Okay, we're going to go ahead and do one more example, I believe one or two, and I believe it's going backwards. So let me see. Yes, so we're going to go ahead and do one more of these. Actually, what am I doing for this one? Yeah, we're going to go ahead and try to draw this out, and we're going to draw it, and we're going to come up with a conclusion. So this one's a little bit interesting. It says use an Euler diagram and all of the premises in the following argument to determine a valid conclusion for the argument. So we want to determine a valid conclusion for these two premises. Okay, so we're going to start with our box, which is our universe. Okay, and let's see what we have here. We have that all m's are n's. So all m's are n's. And no n's are p's. Interesting. So we have kind of like 2 and 1 going on here. So let's see how that works. I'm going to start with this one right here, my first premise. We have all m's are n's. So for sure I have these n's, okay? And all of my m's are inside it because it says all the m's are n's, okay? So all the m's are n's, okay? Then it says no n's are p's. So we haven't seen that one yet. If you don't know how to draw that, we can go ahead and look over here and see what that looks like. So here we have that case right here. No this are that, and they're actually 2 separate circles. So that means I'm probably going to have another circle here somewhere. So if none of these guys, my n's, are p's, I'm going to have another p circle over here. Okay, so what can we conclude from this? What's something valid that we can conclude? Well, let's take a dot and put it somewhere. Let's see. If I put a dot, let's say right here, all I can say is, well, I know that that dot is I know it's an n, but that's about it. I really can't say anything that refers to, I don't know if it's going to be an M and N or if it's going to be just N. I really don't know. So I'm not going to go with that because it's kind of unsure. Okay, now let's say if I put a dot right here in the middle, well, I know for sure that this is an M and it's an N. I also know that it's not going to be a P. Does that make sense? So I'm going to conclude to include all of what I have here that since no N's are P's, no M's are P's either. Okay? And that's an example of something you could use that's a valid conclusion. We're going to try one more with a different quantifier. Okay? So again, we're going to draw our universe while we read that. It says some rabbits are white. All white animals like tomatoes. Therefore, what can we conclude from that? All right, so let's go right into it. Some of these guys are white. So let's draw our circles. We have white, and we have rabbits, and it says some. Remember, some means that they're going to intersect at some point. And again, if you don't remember, you can always refer to the diagram. So these are the rabbits. So some of these guys are white, so that would be in this part right here. Okay, and then it tells us that all white animals like tomatoes. So we have another circle we're going to have to look at here. Let's use this color. So these guys also like tomatoes. So you kind of have to do another circle where all of the white animals are inside this one because they all like tomatoes. So I'm going to do another circle kind of like so here. And this would be the tomato part. So let's see if this makes sense and make sure we're on the right track here. So some rabbits are white. So we have that. We have that intersection right here. All white animals like tomatoes. So my circle for white is inside the circle for tomato, which makes sense because all of these guys have to be inside that guy. What can we conclude from here? Well, if I want to include everything that I know so far, how about I can say that if I have a rabbit that's in this part right here, okay, well, I know it's white, I know it's a rabbit, but remember that all white animals are also in this bigger circle. So what can I say about that? I can say that I'm going to put it here so you can see it. Some rabbits like tomatoes because they're in that tomato circle also. And that's it. That proves it that it's valid. I think that's it, guys. So if you have any questions, let me know. You won't have too many homework problems for this section, but if you do need help, like I said, just reach out to me and I'll help you out, okay? Thank you.